Do you think you understand what light is? You probably do. It's what illuminates your room, carries the colors of the rainbow, travels at 186,000 miles per second. Physics solved this a long time ago. It's an electromagnetic wave. It's in the textbooks, in Maxwell's equations, in 2 centuries of experiments, solved. But it isn't. There is one experiment, a single experiment, that demonstrates something that should not be physically possible. Light behaves like a wave and a particle at the same time, not metaphorically, not in a certain sense. In real experiments, with measurable results that directly contradict each other, the wave produces interference patterns. The particle produces discrete detection events. These 2 behaviors are mutually exclusive in classical physics. They cannot coexist in the same object, and yet they do. The standard answer you've probably heard is, it's quantum weirdness, just accept it. That is not an answer. It is a capitulation disguised as an explanation. Richard Feynman had a better answer, one that doesn't ask you to accept the contradiction, one that dissolves the contradiction by replacing the wrong question with the right framework. But to get there, you need to truly feel the paradox, not the softened textbook version, the version that kept the greatest physicists of the 20th century up at night. Here is the problem in its most naked form. When you place a barrier with 2 slits in front of a beam of light and measure the result behind it, you get an interference pattern, alternating bands of light and darkness, like waves adding and canceling each other. That is wave behavior. When you point that same beam at a sensitive detector, it records discrete events, one by one, each photon striking a specific point, like a bullet hitting a target. That is particle behavior. These 2 results are not theoretical hypotheses. They are experimental results. Both are correct. Both are real. And they describe behaviors that should be mutually exclusive. The wave exists distributed across all of space at once. The particle exists concentrated at a single point. One thing cannot be both, unless it can. 2 centuries of physics tried to resolve this. I'm going to show you how every attempt failed, and why Feynman's attempt is different from everything that came before. The history of light is an intellectual war that lasted nearly 200 years. And what makes this war fascinating is that both sides were right, each with their own evidence, each with their own experiments, each correct and, at the same time, profoundly wrong. Isaac Newton was on the side of particles. For Newton, light was composed of corpuscles, tiny particles that traveled in straight lines. This explained reflection with simple geometry. The particle strikes, bounces, exits at an angle equal to the angle of entry. It explained refraction, particles changing speed as they entered a denser medium, altering their trajectory. The model worked. Newton was Newton. Nobody was going to challenge that easily. But Christian Huygens disagreed. For Huygens, light was a wave, a disturbance propagating through space, like sound in air or ripples on the surface of water. And his model also explained reflection and refraction. The problem is that with 2 models explaining the same things, how do you decide which one is correct? You need an experiment that produces different results depending on which model is true. In 1801, Thomas Young did exactly that experiment. He took a beam of light, passed it through 2 parallel slits, and observed the pattern projected on a screen behind them. If light were particles, you would expect 2 bands, one for each slit, like bullets passing through 2 holes. What Young saw was completely different. He saw an interference pattern, alternating bands of light and darkness, spreading across the entire screen. It was unmistakably the pattern that waves produce when they meet. Constructive interference where peaks align, destructive interference where peak meets trough. This was not the behavior of particles. It was, beyond any shadow of a doubt, the behavior of waves. The waves won. The war was over. And then, in 1865, James Clerk Maxwell put the final point on it. Working with equations that describe electric and magnetic fields, Maxwell realized something extraordinary. An oscillating electrical disturbance generates an oscillating magnetic field, which generates another electric field. which generates another magnetic field, cascading, propagating through space at a calculable speed. He calculated that speed. It was 186,000 miles per second. Exactly the speed of light. Light was an electromagnetic wave, literally, an oscillation of electric and magnetic fields propagating through space. Maxwell's equations described this with mathematical perfection. For 40 years, that was the answer. Physics was solved. Physicists at the end of the 19th century were so confident that the basic framework of nature was complete that some even suggested the work of young physicists would be merely to refine the decimal places of measurements. The Great Revolution had already happened. The nature of light was understood. And then came a 26-year-old working as an examiner at a patent office in Bern, who inadvertently destroyed all of it with a single paper. The year was 1905. Albert Einstein published not one, not two, but 5 revolutionary papers in that single year. But here's something most people don't know. The Nobel Prize Einstein won was not for special relativity. It was not for general relativity. It was for a phenomenon that seemed far more mundane, the photoelectric effect. This detail matters, because the photoelectric effect was the experiment that made the wave-particle paradox officially unsolvable within classical physics. What is the photoelectric effect? Simple in description. When you shine light on a metal, electrons are knocked off the surface. This phenomenon was known. What wasn't explained was the specific pattern of how it happened. According to wave theory, the energy of light is distributed continuously throughout the wave. A more intense wave carries more energy. So if you increase the intensity of the light, make it brighter, you should knock out more electrons, and with more energy. And if the wave were very weak, it might take a while to accumulate enough energy to knock out an electron, but eventually it would. The frequency of the light? Irrelevant. What matters is the intensity. But that's not what happens. What the experiment shows is the opposite. Below a certain frequency of light, no electrons are knocked out. No matter how intense the light, no matter how long you shine it. 0 electrons. But above that threshold frequency, even very faint light knocks out electrons immediately with no delay at all. And the energy of the ejected electrons depends on the frequency of the light, not the intensity. This is impossible if light is a continuous wave. Einstein proposed the solution. Light is not a continuous wave. It comes in discrete packets of energy, quanta of light, what we now call photons. Each packet carries energy proportional to frequency, not intensity. Below a certain frequency, the energy packet is too small to knock out an electron. Above it, each packet has enough energy, and the electron is ejected immediately. It was elegant. It was precise. It perfectly explained the experimental data. But it created a catastrophic problem. Young proved that light is a wave with the double-slit experiment. Maxwell proved that light is an electromagnetic wave with his equations. Those results were not wrong. They continued to be reproducible, verifiable, correct. And now Einstein was proving that light was also particles. Einstein's Nobel in 1921 was not awarded lightly. The Nobel Committee waited 16 years after 1905 to be certain enough to recognize the photoelectric effect. When they did, they were validating not just the result, but the reality of the photon, the experimental proof that light had a particle nature. 2 experiments, 2 results, both correct, directly contradicting each other. From that moment on, physics had a real problem, not an apparent paradox, not a semantic question. A genuine experimental contradiction, with solid evidence on both sides. And then things got even more unsettling. Go back to the double-slit experiment. This time, let's understand it completely. The setup is straightforward. You have a light source, a barrier with 2 slits, and a detector behind it. The question is, what do you see on the detector? If light were particles, the reasoning is direct. Each particle goes through one slit or the other. Not both at the same time. That would be absurd. So you'd expect to see the accumulated pattern of particles passing through slit 1, plus the pattern of particles passing through slit 2. 2 bands. Simple. If light is a wave, the reasoning is equally direct. The wave spreads through both slits simultaneously, emerges from both sides as two separate wave sources, and those two waves interfere with each other. Where peaks align, constructive interference, bright light. Where peak meets trough, destructive interference, darkness. You get the alternating stripe pattern that Young measured in 1801. The experiment shows the interference pattern, established. But then, physicists did something that changes everything. They dimmed the light source until it was emitting only one photon at a time. Experiments carried out with complete rigor from the 1970s onward. Literally, a single packet of light, individually, fired toward the slits, with the detector recording where each one arrived. You'd expect that without two simultaneous waves, there would be no interference. One photon goes through one slit, one dot on the detector, another photon, another dot. Over time, two clusters of dots, one for each slit. What actually happened was this. The first photons arrived at seemingly random positions, then a few more, then more still. And as hundreds and then thousands of photons accumulated, one by one, a pattern emerged on the screen. The interference pattern. A single photon was interfering with itself, as if it were passing through both slits at the same time. This is physically baffling at a level that words barely capture. A particle cannot be in two places at once, but the experimental pattern demands that it behave as if it were. And then physicists had the obvious idea. Let's find out which slit the photon goes through. Just place a detector at each slit, something that registers when a photon passes by. That way you know the path. Problem solved. They did exactly that. The interference pattern disappeared. When you observe which slit the photon passes through, you get what you'd expect from particles. Two clusters of dots, one behind each slit. No interference, no stripes. Pure particle behavior. Remove the detector from the slits, the interference pattern returns. Put it back, it disappears. This is not a technical problem. It is not a matter of the detector disturbing the photon in some mechanical way. Physicists built progressively more sophisticated, more delicate detectors. It made no difference. The act of measuring which path the photon takes, regardless of how you measure it, destroys the interference pattern. The photon seems to know it is being observed. This became known as the measurement problem. And for decades, it was considered the deepest paradox in physics. Not merely, light is strange, but observation changes what happens. Reality appears to behave differently depending on whether or not it is being measured. Einstein spent years trying to prove there was a more sensible explanation, that the photon had some hidden property that determined in advance which slit it would pass through, and that quantum physics simply didn't have access to that information yet. Hidden variables, an underlying reality that would make everything deterministic again. Niels Bohr disagreed, and then things got philosophical in a way that physics rarely does. The 1920s produced quantum mechanics, one of the most successful mathematical frameworks in the history of science. And with it came an interpretation of that formalism that dominates textbooks to this day. The Copenhagen interpretation, associated primarily with Niels Bohr, states the following. A quantum object, an electron, a photon, has no defined properties before it is measured. It exists in a state of superposition, potentially in multiple places, with multiple values of any measurable quantity at the same time. When you make a measurement, the wave function collapses. The system jumps to a single definite state, and you get a result. Mathematically, this works. The predictions are correct. Standard quantum mechanics makes predictions that match experiments with extraordinary precision. But what exactly is a wave function? What is a collapse? What does it mean to say the electron has no definite position before being measured? Bohr had an answer. His position, in plain terms, was, these questions are meaningless. Asking where the photon is before measurement is like asking what the temperature of a flame is before fire exists. The question presupposes an existence that the phenomenon does not authorize. Quantum reality is fundamentally about what you can measure, about relationships between measuring devices and quantum systems, not about objects with independent properties existing out there on their own. Einstein hated this. The debates between Bohr and Einstein are legendary in the history of physics. Einstein would present elaborate thought experiments, hypothetical scenarios constructed to demonstrate that the wave function had to correspond to some underlying physical reality. Einstein would wake in the middle of the night at the Solvay conferences to mount new attacks on the quantum formalism. Bohr would appear at breakfast with the answers ready. For 3 years, Einstein found no opening. And that should have ended the debate, but it didn't. Because even while being defeated in the calculations, Einstein was asking the right question. History generally casts Bohr as the winner of these debates. But Einstein was never satisfied, and there is a good reason for that. The Copenhagen interpretation works as a recipe. It tells you what to calculate and how to calculate it. But it does not tell you what is happening. It describes the phenomenon without explaining it. The phrase that became famous for describing the dominant philosophy of quantum physics in the 20th century is, "Shut up and calculate." Don't ask what the wave function means physically. Don't ask what happens during a measurement. Just apply the rules, get the right numbers, and be happy. For decades, this was considered sufficient. After all, quantum mechanics works. The numbers add up. For practical purposes, that is what matters. But there is a deep philosophical problem with this stance. A theory that tells you what happens without telling you why is a description, not an explanation. It is like saying the sun rises in the east because it always rises in the east. Correct. Completely useless for understanding the underlying reality. The Copenhagen interpretation is the most precise map ever made of a territory it refuses to describe. There was a third way. Not Bohr's surrender, not Einstein's frustrated hope, a mechanism. Richard Feynman won the Nobel Prize in Physics in 1965, shared with Julian Schwinger and Shinichiro Tomonaga, for quantum electrodynamics, the quantum theory of interactions between light and matter. But what defines Feynman as a physicist is not only the prize, it is the way he thought. While most physicists of the era were content to work within the existing formalism, Feynman insisted on understanding. Not merely calculating, understanding. What is the mechanism? What is nature actually doing, moment by moment? His lectures at Caltech, published in 1964 as the Feynman Lectures on Physics, are considered some of the finest physics texts ever written, not only for their mathematical quality, but for their intellectual honesty. Feynman did not artificially oversimplify, but he also did not hide real difficulties behind impenetrable technical language. And it was in his lectures and writings that he made a statement that changed the way an entire generation of physicists thought about the problem. If you think you understand quantum mechanics, you don't understand quantum mechanics. This is not performative modesty. It is a precise technical statement. Quantum mechanics works. Its predictions are correct. But no one, including the physicists who use it every day, has a satisfying intuitive picture of what is happening at the quantum level. The mathematical tools exist. The deep physical understanding does not. But Feynman went further than simply admitting the confusion. He reframed the question. Most approaches to wave-particle duality ask, what is light? A wave? A particle? Both? Neither? Feynman asked something different. What does light do? What rules does it follow to get from one point to another? This shift in question is, in itself, a profound insight. Because what is light presupposes that there is some essential nature, some kind of thing that light is in the classical sense. But perhaps the right question is not about nature, but about behavior, about the mechanism. Feynman's answer to that question is what became known as the path integral formulation. And it does something the Copenhagen interpretation never did. It describes what light is doing, geometrically, mathematically, moment to moment. Here is the idea that will seem absurd for the first 5 seconds, and that will shortly make everything we have discussed so far seem inevitable. When a photon, or any quantum particle, travels from point A to point B, it does not take one path. It takes every possible path simultaneously. Not takes the most likely path. Not takes a path we don't know. Every path. The straight path. The path that detours past Mars. The path that loops all the way around the universe before arriving. All of them. At the same time. This sounds absurd, and in classical terms it is. But Feynman did not stop there. The next question is, how do multiple simultaneous paths produce a single result when you make a measurement? The answer lies in how the paths combine. For each possible path, you assign a probability amplitude, what Feynman called a spinning arrow, a phase. Imagine a clock hand. Each path has its own hand, spinning at a rate that depends on how long the path takes to traverse. When the photon reaches its destination, you add up all the amplitudes, all the hands, as vectors. Where many paths arrive with their hands pointing in the same direction, the amplitudes add together. This is constructive interference, a high probability of the photon being detected there. Where paths arrive with their hands pointing in opposite directions, the amplitudes cancel. This is destructive interference, low probability, or zero, of detection there. You have just watched the interference pattern emerge from arithmetic, not from some magical property of light, from hands that add up or cancel out. Let that mechanism settle for a moment, because what comes next is where everything clicks into place. The double-slit interference pattern is not mysterious in this context. The two slits represent two sets of possible paths. One set passes through slit 1. The other set passes through slit 2. For each point on the detector, you sum the amplitudes of all paths arriving there, both those that pass through slit 1 and those that pass through slit 2. Depending on the geometry, on how different the lengths of those paths are, the two sets of amplitudes can reinforce or cancel each other. This produces exactly the stripe pattern you observe, not because the particle chose to be a wave, but because every possible trajectory contributes and their amplitudes interfere. Now the measurement problem. Why does placing a detector at the slits destroy the pattern? Feynman's answer is surgical. Once you understand it, the measurement problem never looks the same again. When you place a detector at slit 1, you are determining which path the photon took. More specifically, you are eliminating all paths that pass through slit 2. Think of the spinning hands. When you block half the paths, you remove from the sum all the arrows that passed through there. The detector selects a subset of paths, only those passing through slit 1, and discards the rest. But when you eliminate half the paths, you eliminate half the amplitudes. And when you have only one set of amplitudes, only the paths through slit 1, or only through slit 2, there is nothing to interfere with the other set. Without two sets of amplitudes, no interference. Without interference, no stripe pattern. You get two clusters of dots, exactly what you would expect from particles. The detector is not mechanically disturbing the photon. It is not collapsing anything in some mysterious way. It is simply selecting which paths exist in the calculation. It eliminates the others, and without the others, no interference. That is the click of the lock. Wave behavior, the interference pattern, is what you see when many paths contribute amplitudes that interfere constructively and destructively. Particle behavior, a discrete detection event at a single point, is what you see when the calculation is forced to select a specific outcome, whether by a measurement or by the experimental geometry. Wave and particle are not two natures of the photon. They are two different aspects of the same underlying calculation, visible under different experimental configurations. And the wave function, the mysterious object that collapses in the Copenhagen interpretation, it has a concrete interpretation in Feynman's formalism. It is the sum of amplitudes over all possible paths. It is not an ethereal entity floating in space. It is a mathematical object that encodes all possible trajectories and their relative weights. Feynman expanded this structure to create quantum electrodynamics, QED, the complete theory of how light and matter interact. The so-called Feynman diagrams, which you have probably seen in books or on t-shirts, are simply a visual notation system for organizing these path sums, a computational shortcut, not the physics itself. The physics are the amplitudes, and what QED delivers with these amplitudes is not merely an elegant conceptual framework, but a precision tool without precedent in the history of science. Here is a number: 10 decimal places. The magnetic moment of the electron, a fundamental property of how electrons interact with magnetic fields, was calculated using QED and measured experimentally, independently. The theoretical result and the experimental result agree to 10 significant digits. To grasp what this means, it is equivalent to measuring the distance from New York to Tokyo with an accuracy of less than 1 millimeter. No other theory in the history of physics has come close to this level of predictive precision. Not general relativity, not the standard model of particles. QED is, by any reasonable empirical standard, the most verified theory humanity has ever produced. When someone says, "But it's just a mathematical interpretation about the path integral formulation," that number ends the discussion. Nature does not behave this way approximately. It behaves this way with a precision that has no equivalent in any other domain of science. With that exit closed, we can return to the original question, not to find a simpler answer, but to ask it more honestly. Wave and particle are classical concepts. They arise from our experience with macroscopic objects, billiard balls, ocean waves, sound waves. They are useful categories at the scale we can see and touch directly. But asking whether a photon is a wave or a particle is like asking whether the number 3 is red or blue. The question seems grammatically coherent, but the concepts simply do not apply to the object in question. 3 has no color, and photons are neither waves nor particles. They are photons. They are quantum objects, and quantum objects simply do not fit into the categories we developed by observing the macroscopic world. The paradox does not exist in nature. It exists in the vocabulary we chose to describe nature. So what is Feynman's real answer? It is not a definitive solution. He was the first to say he did not have one. What he did was something epistemically more valuable. He did not solve the paradox, he dissolved it. He revealed that the paradox was not in nature. It was in the vocabulary we chose to describe it. Copenhagen tells you what happens and asks you not to ask why. Feynman tells you the mechanism, and then tells you precisely where the mechanism meets its own limits. That distinction is the difference between a physics that closes in on itself and one that remains honestly open. The difference is fundamental. An explanation gives you power. You can reason from it, extend it, test it in new scenarios. A redescription leaves you exactly where you started. From a single principle, every possible path contributes and the amplitudes add together. Both the interference pattern and the discrete detection event emerge. The duality was not a contradiction of nature. It was a limitation of vocabulary. The deeper question: why does nature sum over all paths? Why do amplitudes exist? Why is the universe this way? Remains open. Feynman had no answer for that, and neither does any other physicist. What he had was enough intellectual honesty to separate what we know from what we do not know, and enough technical sophistication to push the "we don't know" to the most fundamental level possible. This is what genuinely good physics looks like. Not the false certainty of its quantum weirdness. Accept it. Not the capitulation of shut up and calculate, but here is the mechanism. Here is where it meets its limits, and here is why that distinction matters. If you want to go deeper into this framework with Feynman himself as your guide, the book QED, The Strange Theory of Light and Matter, is the right place. Written by him without heavy mathematics, with the same honesty we have seen here. And if this kind of explanation, one that does not hide the real complexity, that does not pretend paradoxes are simple, but that also does not abandon the pursuit of genuine understanding, is what you came here for, subscribe. Not elegant capitulation, real explanation.